Hi, everyone. Welcome back to lecture 3. And now let's talk about higher moments and Chebyshev's inequality. All right. So, okay. Now, if you want to give better concentration bounds, okay, we need more information about the random variable beyond the expectation, right? And here's the example that we talked about in the beginning of the lecture. So let's talk about it again. How do we distinguish between these two random variables, right? Like, so the variable x such that the probability of x equals to I is equal to 1 over n, right? Where I goes from 1 up to n and 0 otherwise. And the other random variable y, that is probability that y is equal to 1 is a half, probability that y is equal to n is a half. So if we draw those pictures, right, like those random variables, we have that x, if we have the value here, we have maybe, let's say, 1, 2, 3, all the way up to n. Well, what will be x? X will be exactly, I have 1 over n here, right? So x is going to look like something like this, right? So this is random variable x, and then we have random variable y, which is what? Well, here now we have probability a half, right? And then we have 1, and we have n. So, and then our concentration, like our variables concentrated here in those two variables, right? So these random variables look very different. Do you agree? So, all right, how do we distinguish, like, mathematically, like, you know, like, based on the picture, you can see that they're different, right? But now, how would you mathematically distinguish between those probabilities, those random variables, right? So the way to distinguish them is the following, right? So they have the same expectation, right? But they're very different random variables. Now, all right, so if we look at how far, okay, the variable usually is from its expectation, that's really what we want to look for, right? Because this is one of the many, like, different ways in which these two random variables behave, right? Like, one random variable is never close to its expectation, and the other one is, well, you know, it behaves kind of uniform, right? Like, so you have the expected value uniformly, you can find more and more values as you go far away from the expectation, right? So this is one way of distinguishing those two. So we need to look at how far a variable usually is from its expectation. Now, how do we do that, right? So, all right, so how far x is from its expectation, right? Well, this is actually quite easy because we can just bound, like, the absolute value between x and the expectation of x. This is a measure of how far I am from my expectation, correct? So, okay, so what we can do is we can try to compute this expectation, right? So at a first glance, we can try to compute the expectation of this new random variable, right? Like, this is another random variable. So now, if we compute this expectation, right, we have, like, we would expect that if we're close, if the variable is always close to its expectation, then this new random variable has a small expectation, right? And if I'm always far from the expectation, then we should expect this quantity to be large. Does that make sense? So that's the intuition, right? So if close to expectation, most of the time, then it's small. But if we're far from expectation most of the time, we should expect this to be large, correct? So this is one way in which you can try to control it, right? And now, now we have the question, well, okay, how do we bound then, if we have this random variable, how do we bound the probability that x, like the absolute value of x minus e to the x, is greater or equal to t? How do we bound this inequality, right? All right. Well, here's the thing, right? And this is the content exactly of Chebyshev's inequality, right? So the probability that for any discrete random variable, the probability that x is t far from its expectation, and t far, I just mean this kind of inequality that you're seeing right now, right, is less than or equal than the variance of x over t squared, okay? So, okay, and for those who don't know what variance is, we're going to learn about it now, and we're going to learn about moments. Okay, so, all right, so let's say, let's x be a random variable. Okay, so what its variance, the variance of random variable x is defined by the symbol bar x, which is equal to the expectation of the random variable x minus e, the expectation of x, all of it squared. Okay, and note that, you know, if you note, like the absolute value of x minus ex, right, is just can be derived from this other random variable like x minus ex, all of it squared, right? Because you just take the square root, okay? But its variance is defined as this expectation, and its standard deviation, which is something you probably heard a lot, right, is the square root of the variance. Okay, so now, how do we prove Chebyshev's inequality, right? So the way we prove Chebyshev's inequality is by what? What is the only tool that we have at our hands right now, right? If this is the first kind of class on concentration inequalities you're having, what is the only inequality that we know? We only know
Markov.
Exactly, we only know Markov. So let's use it, right? So the idea here, again, we only know Markov. So let's use it. Right? So how do we use it? Which random variable should we use for Markov?
X minus the expectation of x.
Sorry?
X minus expectation of x.
Right. Okay. So let's try here. So let's write my random variable here, x minus the expectation of x. Okay. Can I use Markov with this random variable?
You need to take absolute value.
Right. So the first thing is that this random variable is not non-negative all the time, right? So we cannot use it. So one suggestion is that we can take absolute value, and you know, another one which may be a little bit easier for computations is that it's just a square, because square of any number is non-negative. So let's just use this random variable. Okay. So now note that y is discrete, right? Is discrete if x is discrete, correct? And this is also greater or equal to 0, right? So therefore, we can use Markov here. So can use Markov. Okay, yes?
T doesn't have to be a natural number. Be any
No.
non-negative real number.
Yeah, it can be any non-negative real number, and maybe like I just wrote the proof for like to make it easier on notation. But if we go back, let me just go back to the proof. Like the way to adapt the proof, like what is the thing that we used in the proof of Markov's inequality? All we did is that any value that is less than t, we made the probability of that event. We just said that probability is greater or equal to 0, right?
Right.
And
then, but we were
well,
sort of summing over natural numbers. No?
Yeah, because I mean, a discrete random variable is a random variable that takes values over a discrete set, like a1 up to a, you know, what over the natural numbers, right? Like this is a discrete random variable. So your set is a countable set. Okay.
Right. Yeah.
You can say that like here I just made it sure.
Oh, you're doing it like a disjoint union type.
Well, a discrete set is a set of this form, right? So
yeah,
that's all. But just to simplify notation, I just assume that each of the AIs, because all the AIs are different here, right? So all AI is different.
Yeah, otherwise, yes.
Right, because Otherwise, they're the same event. Does that make sense?
Yeah.
Yeah. And then in this proof here, all we did is like, yeah, the only thing we did is every AN that's less than or equal to T, I'm just going to set the probability to 0. And every AN that's greater or equal to T, I'm going to set the value AN greater or equal to T. Right? So that's the
Wait
only
a minute,
thing.
though. In general, though, how do I know there's only finitely many of them?
You don't need to have finitely many.
Oh, because, oh my God. See, this is really getting me to think about stuff I haven't thought about.
Okay. So yeah, in this case, for example,
yeah.
was a case that we didn't have finitely many. So
I think otherwise there's like probability rules that say it has to converge or something.
no, if expectation of x is infinity, this inequality holds trivially, right? Because E of x is infinity. So your probability is less than or equal to 1. So okay. So that's as simple as that. Like it's just if your expectation goes to infinity, then well, this inequality is not giving you anything, right? So all right. So okay. So yeah. So the proof I did here was just to simplify notation. Okay, but it works for any discrete random variable. Does that make sense? So let me. Yeah, I think that's a great point, because that's why I didn't want to put all of those details, right? Because we don't need to deal with those details. All you need to know is, oh, this is the idea of the proof. The rest is just writing a little bit more math over it. Okay. So okay, is that clear for everyone so far? Yes, any non-negative discrete random variable. Okay. So all right. So then let's go back to our Chebyshev proof. Right? So, all right. So again, we only know Markov, and now we also know that y is a discrete random variable because x is discrete, right? And y is also always non-negative. So here we have exactly the setting of Markov, okay? And now how do we apply Markov? Well, we know that by Markov, what we have is that the probability of y being greater or equal to t squared. And why am I saying y greater or equal to t squared? Because what we really want to bound is the absolute value of x minus the expectation of x, right? So for that, if this is equivalent to saying, okay, I'll get back to that later, but if we use Markov here, we have that this is less than or equal than the expected value of y over t squared, right? That's just what Markov gives us. But now, what is the expected value of y? If you look at the definition of variance, the variance of x is exactly the expected value of y. So this is, by definition, we have the variance of x over t squared. So we're almost there with our Chebyshev. The only new thing that we need to notice is that the probability of this, of y squared greater or equal to t squared, is exactly the same as the probability that absolute value of x minus e to the ex is greater or equal to t, right? Because this is just the same thing as if I squared both sides, right? So, and these are non-negative numbers, right? So if I take two non-negative numbers, right, like a is greater or equal to b, if and only if a squared is greater or equal to b squared, right? So this is equivalent. Those two events are the same. Okay.
I'm confused. Aren't you not forgetting the negative part?
No, right, because we have absolute value, right? So x minus the absolute value of x minus ex is greater or equal to t if and only if like x minus the expectation of x squared is greater or equal to t squared, right?
Right. But no. Why is it if and only if? Isn't only if
No,
if,
it's well, it's if and only if,
because
right?
because
Is this inequality here, right? Like a squared greater or equal to b squared, if and only if absolute value of a greater or equal to absolute value of b.
all right. Right. Yeah.
Okay. Yeah.
Yeah. I was just thought that maybe the negative part you're forgetting, but yeah, the absolute. Okay.
Right. Okay. Excellent. So, okay. So now we have proof Chebyshev, right? And any more questions about the proof? Okay. So, all right. So now let's talk a little bit about more moments, right? And about covariance. Now, how do we measure the correlation between two random variables? Okay, this will come up at some point in our homework and also in real life. We do have to measure correlation between random variables, right? So, well, one way to measure the correlation between two random variables, okay, is the covariance. Okay, so, and the covariance of two random variables is just defined as the expectation of the product of the random variables x minus ex and y minus ey. Okay, so, and we say that x and y are positively correlated if this covariance of x and y is greater than 0, and negative correlated if x and y is less than 0. Okay. So one way to see this is that, well, if the values are positively correlated, if, whenever x is big, y should also be big, right? Like bigger than its average. And whenever x is small, y should also be small. Then you get that they're positively correlated because they're always going the same direction, right? So if one is big, the other one's big. And if one is small, the other one's small, right? This is a proxy measure for it, right? It's not fully capturing all these kind of situations, but is a proxy for it, right? And they're negatively correlated, okay? If this covariance is less than 0, because intuitively what would happen is that whenever x is big, then you should expect y to be negative, right? And whenever, y to be small, like smaller than its average. And whenever y is big, x is small, right? So this is the intuition that the covariance is trying to capture, okay? So, and now here's a proposition and something that we use often, right? Which is, so by definition, and this is something you can prove, that the variance of x plus y is equal to the variance of x plus variance of y plus 2 times the covariance of x and y. And if you think about it, this is really just kind of saying that a plus b squared is equal to a squared plus b squared plus 2 times ab. Okay, that's really, but this also happens with expectation. Okay, so if you just plug in the definitions, you're going to get this. So as a practice problem, you should just prove this proposition. Okay, and if x and y are independent, then we also know that the variance of x plus y is equal to the variance of x plus the variance of y. Okay, so if x and y are independent, then we know that its covariance is 0. Okay, so as a proof, as a practice problem, just prove this. Okay, and if you have trouble with it, you can come to office hours. We can do it together. So, all right, any questions so far? Okay, so, all right, so now let's talk about Chebyshev and our covariance example, right? So let's talk about now the coin flipping example that I asked you to keep in mind, right? So, okay, in the coin flipping example, if x was the number of heads, right, like in an independent unbiased coin flips, then let's try to bound again the probability that x will be greater or equal than 3n/4, right? We got that this value was less than or equal to 2/3 by Markov. Now let's use Chebyshev. So, all right. So if we look at our random variables, let's say that for the ith like coin flip, right? So this is the random variable for the ith coin flip. Right? And now we're going to say, well, in the ith coin flip, xi is 1 if the coin flipped heads and 0 otherwise, right? Because we're trying to count the number of heads. And our random variable x is just the sum of these random variables. And we know that xi and xj are independent, right? For any 2 trials, because those are independent coin flips. So, all right. Now, here's the thing. By the proposition, Okay, what do we know? We know that the variance of x, so if you remember the second bullet of the proposition says that because xi's are independent, right? By proposition, let me put here like second bullet on the previous slide, right? We know that the variance of x is equal to the sum of the variances of each of its components. But what is the variance of one of these variables? Well, the variance of one of these variables is what? Well, what is the expectation? Well, expectation of xi is equal to 1 with probability a half plus 0 with probability a half. So this gives us a half. So what is the variance of xi? Well, what is the definition of variance of xi? Is expectation of xi minus its expectation squared. But what is this expectation? Well, with probability half, I have that xi is equal to 1. So I'm going to get 1 minus a half squared. And with probability a half, I'm going to get that my random variable is 0 minus the expectation, which is half squared. Correct? But both values are giving me 1/4, right? So this is exactly 1/4. Now, we know that each of these variants of xi is 1/4. So when I sum n copies of those, I get n over 4. Does that make sense? So this is the variance of these random variables. So second bullet, and independent, we use independence. And now, if we use Chebyshev here, what do we get? What is the probability that x is greater or equal than 3n over 4? This probability is less than or equal than x minus n over 2, which is the expectation of x is greater or equal than n over 4, right? Because the second event here contains the first one, correct? So it's a bigger event. Does that make sense? So, all right. So then we know that this inequality holds because of a bigger event. So let me just put it here for you to remind, like bigger event space. And now, right, we can use Chebyshev's, right? So the second inequality here is Chebyshev, which gives us, well, this is the variance and this is the value of t squared, right? So now we have exactly 4 over n. Okay, so again, we went from the probability of x greater or equal to 3n over 4 being less than or equal to 2/3. It's actually less than or equal than 4 over n. So you can see the improvement that we have over Markov, right? Does that make sense? So just keep that in mind, right? So, all right. So then you notice now that, oh, if I know the variance, I'm able to use Chebyshev. So it is a stronger inequality than Markov, right? So if you want to have even more information of a random variable, it's very useful to look at more of its moments. Okay, and what are its moments here? Well, we're going to define the moment, like the kth moment of a random variable x, okay, is the expectation of x to the power of k. Right? And why is that? Why would that give you more intuition? Is because, remember, suppose that if I have, like if my variables are always far from expectation, right? That there's going to be really big numbers and small numbers. But then if I square them, the big numbers become much bigger. So they get much further away intuitively from the expectation, right? So if we study these moments, like if we put things to higher powers of k, we're able to kind of magnify like how far they will be from the expectation, right? So this is the idea for studying like the kth moments. And another one, which is actually what we used, right, for the variance, is the kth central moment of a random variable, right? So the kth central moment of a random variable is just take the random variable, subtract the average, right, which is the expectation, take this to the power k, right? So for example, and this if exists, of course, right? And we know that, like, let's say mu2 of x is exactly the variance. Does that make sense?
I have a question.
Sure.
K equals 1 here does not make sense, right? Because it's just gonna be 0.
No. K for the central moment.
Yes.
No,
Because
it makes sense. It's just 0.
right, but it doesn't help much because maybe even like X could be far away from the expectation.
Yeah,
Like,
exactly.
But so it doesn't help or it gives information. That's why we look at the variance, right?
Exactly. X equals to 1. This random variable will be equal to 0 for any random variable. So you're good. So this doesn't give you any information. But now you
Right.
take K equals to 2. This is like, this already gave us the variance and gave us Chebyshev, right? So the
Okay.
idea is like, well, what if we use for higher K? Can we get like more difference, right? And the answer is yes.
Because I thought you wrote the equation with K equals 1 up like in the top of the thing, and then I got confused. Yeah.
Sorry,
So-
where is it equal to 1?
I don't remember, like at the really beginning, when you started speaking about Markov, I think. But yeah, so I got confused. But
Oh, okay. No, sounds good. So, all right. So far, so good. Okay. So now, and here's the idea. Oh, 1 second. I need to charge my computer. Okay. Sorry. All right. I want to die. All right. So Chebyshev's inequality here, right? Notice that it's most useful when we only have information about the second moment of the random variable x, right? If we can get the second moment, then we can use Chebyshev because the second central moment is exactly the variance, right? So, all right. Now here's the practice problem, right? So can you generalize Chebyshev's inequality to the kth central moments, right? So what is the inequality that we're going to get? Okay, and for which case is it valid, right? So as Hazem noticed, okay, for k equals 1 is not valid, like, but for what other case is it useful, right? So, or even valid. Okay, so this is another practice problem. And now let's go to the third part of the talk of the lecture, which is to study the Chernoff-Hefting inequality. Okay, so